Hello everybody, good morning. Myself, Dr. Shubhankar Sen from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the 5th lecture of Module 6 of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall discuss on the stationary iterative methods. We shall briefly introduce the concepts of preconditioners as well as matrix-free methods in context of finite element applications. So first we begin with the stationary iterative methods. The linear matrix equation system is given as Ax equals to B. So finding x amounts to invert the coefficient matrix capital A and take a matrix vector product. Effectively, x equals to A inverse B. So, whatever the steps we follow in the direct methods such as Cramer's rule or Gauss elimination, or in the iterative methods such as Gauss-Seidel, Jacobi, conjugate gradient or GMRS methods, these are equivalent to performing the inversion of the given matrix and taking the product of this inverse matrix with the right hand side load vector. So first we introduce the concept of stationary iterative methods. The stationary iterative methods have constant iteration matrices. In methods like Gauss-Seidel or Jacobi, the DOF at the pth level of iteration may be represented as T p plus 1 equals to H into T p plus C, where T is the DOF, H is the iteration matrix, the vector C is a function of both the coefficient matrix A and right hand side load vector B, and P is iteration count. So we say this is P plus 1th iterate. This may be represented as T at P plus 1th iteration level. This is n by 1 vector. H is the iteration matrix. This is of n by n size. And Tp, this is the n by 1 vector at the pth iteration count. And C is the n by 1 vector. So the iteration matrix, if it remains constant during the iteration steps, or the entries of the iteration matrix, if they do not change with the iterations as they continue, we say that we are dealing with a stationary iterative method. In contrary, in the non-stationary iterative methods such as conjugate gradient, biconjugate gradient, as well as the generalized minimal residual solvers, the iteration matrix has variable entries. If the entries of the matrix H do not change with change in P or iteration count the given method is known as stationary iterative method. Gauss, Seidel, Jacobi methods are examples of stationary iterative methods. If entries of the iteration matrix H alter with iteration count P, the iteration method is known as non-stationary iterative methods. The examples of such methods are conjugate gradient for symmetric positive definite matrices and BICG or GMRES for asymmetric matrices. Now we illustrate the development of the stationary iterative methods. So consider the matrix equation system Ax equals to B or Aij xj equals to Bi for the ith linear algebraic equation. Aij xj equals to Bi, this may be represented as Aii xi plus summation of Aij xj, where j is varying from 1 to n such that j excludes the diagonal term or j is not equals to I. This is equals to Bi. Then we can separate the diagonal term from the off diagonal terms. So this is contributed by the diagonal term, and this second portion, this is contributed by the off diagonal terms. We can shift the off diagonal terms to the right hand side, and then we can get a simplified form as Aii xi equals to Bi minus summation of Aij xj for j equals to 1 to n and j is not equals to I. We can again write it as xi equals to 1 by Aii into Bi minus summation of Aij xj, j equals to 1 to n, where j is not equals to I. So this is the generic form of the solution method of a stationary iterative method. So this is generic form for the DOF during iteration in a stationary iteration cycle. Now let us introduce the iteration count P. So let us introduce the iteration count P. Then we can get the latest solution with P plus 1 index in the left hand side as xi at P plus 1th iteration level equals to 1 by aii into bi minus summation of aij xj at the pth level j equals to 1 to n, j is not equals to I. We can divide by the diagonal term only when the diagonal term is non-zero. It means that this is compulsory that aii must be non-zero. And then when we use this kind of a relation, then we say that we are dealing with the Jacobi method. So in the right hand side, all the terms are treated as the known terms, and the left hand side is giving us the unknown degree of freedom at the latest value. So P plus 1, this gives the latest iteration count. P is the previous iteration count. So during the Jacobi iteration method, the rate of convergence is poor because we use all the solutions from the previous iteration. An upgradation of the Jacobi method is known as the Gauss-Seidel method, where we use the latest solutions available in our right hand side portion, and this increases the rate of convergence in the Gauss-Seidel method. It is double the rate of convergence of the Jacobi method. So we can rearrange or restructure the right hand side portion. The RHS of Jacobi method may be rearranged as xi p plus 1 equals to 1 by aii into bi minus summation j equals to 1 to I minus 1 aij xj p plus 1 minus summation over j equals to I plus 1 to n aij xj p. This modification of this matrix product or the matrix vector product, it results in significant improvement of the convergence rate using the Gauss-Seidel method. So in this case, this is modification in the known iterate values in the Gauss-Seidel method. So the first one is Jacobi method, we have already mentioned, and then the Gauss-Seidel method. The Gauss-Seidel method gives xi at p plus 1 equals to 1 by aii into bi minus summation j equals to 1 to I minus 1 aij xj p plus 1 minus summation over j equals to I plus 1 to n aij xj p. So xj p plus 1, these are the latest available solutions for x or temperature, and here xjp, this is the solutions available from the previous iteration. So this Gauss-Seidel method, it has to satisfy the Scarborough criterion, which talks about the diagonal dominance. The Scarborough criterion is a condition that seeks diagonal dominance of the coefficient matrix while implementing the Gauss-Seidel method. The condition is absolute value of the diagonal term, it should be greater than equals to summation of the absolute value of the off diagonal terms. J equals to 1 to n, j is not equals to I, at least for one row. It means that this Scarborough criterion suggests that at least one of the row in the matrix should be diagonal dominant so that we get converged solution of the Gauss-Seidel solver. Now, this Scarborough criterion, it is a necessary condition but not a sufficient condition, and because of that we can sometimes find solutions that converge even not satisfying the Scarborough criterion. The Scarborough criterion is necessary but not sufficient, and hence converged solutions are still achievable even by violating the criterion. The Jacobi method has the following iteration matrix H. Let A equals to a lower triangular matrix, a diagonal matrix, and an upper triangular matrix. So in that case, it is found that H equals to D inverse L plus U with minus sign, and C equals to D inverse B. So we can write the iterate as T or X at P plus 1 equals to H T at pth level plus C equals to minus of D inverse L plus U into Tp plus D inverse the right hand side load vector for Ax equals to B. The final solution of the Gauss-Seidel method or the Jacobi method, they depend on the convergence criterion. So these iterative methods, they work on the repetitive calculations. So we have to check the convergence of the solutions starting from the initial guess. Starting from the initial guess the solutions evolve till convergence. The convergence is tested in terms of error epsilon or residual r. The error is defined as epsilon equals to the difference between the degree of freedom at a given location at two different iteration counts. It means that if x is the degree of freedom, so x at p plus 1 minus x at p at a given location gives us the error at that location or the node. The residual is defined as Rp equals to b minus a xp. We can test convergence relative to the global error such that absolute value of x at a given node at the p plus 1th iteration level minus x at the same node at the pth iteration level, then we sum it up for all the nodes in the mesh, summation over I node equals to 1 to num n p. This should be less than the tolerance value. For example, we can take it as 10 to the power minus 6. This is defined as error tolerance, or we can define the maximum error in an iteration. So this can be represented as maximum of x inode at p plus 1th level minus x at the same node at the previous iteration. It should be less than 10 to the power minus 6. So this is based on maximum error criterion. The convergence rate of Gauss-Seidel method can be further improved by using a relaxation parameter. The convergence rate of Gauss-Seidel method can be improved by incorporating a relaxation parameter. That is denoted by the symbol omega. The value of omega is based on experience. Kahan in 1958 suggested that the value of relaxation parameter between 0 and 2, it gives us good convergence. For good convergence, if omega is less than 1, we get under relaxation. This is used for nonlinear partial differential equations. If omega, if this is greater than 1, we get over relaxation. This is used for linear PDEs or ODEs. And if omega equals to 1, the method is known as Gauss-Seidel. Now, incorporating this omega, the degree of freedom that we obtained at the p plus 1th iteration, it can be represented as x at p plus 1th level equals to 1 minus omega into x at pth level plus omega into x at p plus 1th level. So this gives us 1 minus omega into x at p plus omega x at p plus 1. We already got it as 1 by aii into bi minus summation of aij xj at p plus 1th level minus summation aij xj at the pth level, where j is varying from 1 to I minus 1, and here j is varying from I plus 1 to n. So this is xi, this is xi, this is xi, so this is xi. So this is the SOR method, also known as the successive over relaxation method. The x equals to b system for heat conduction problems is associated with diagonal dominance of the coefficient matrix A. However, in the convection diffusion problem, the diagonal dominance depends on the differencing scheme used or the finite element formulation used. For the convection diffusion problem, diagonal dominance of the coefficient matrix A depends on the FEM formulation. For such problems, A is diagonally dominant if upwinding or Petrov-Galerkin FEM formulation is used. For Galerkin formulation of convection diffusion equation, matrix A is not diagonal dominant, in such cases the Gauss-Seidel method is found to diverge. Now, we briefly introduce the concept of matrix preconditioners. The preconditioners are square matrices, or these are transformations used for improving the condition number of a matrix equation system. The preconditioners are matrix operators or transformations used to improve or lower the condition number of a matrix in a given matrix equation system. Preconditioning is predominantly used in the iterative method. The preconditioners are widely used in Krylov space methods to accelerate the rate of convergence or to yield stable results in lesser number of iterations. In a matrix equation system, the condition number represents the stability of the equation system. So, with respect to perturbations in the right hand side load vector B, the changes in the degree of freedom vector is dependent on the condition number. In a matrix equation system of high condition number, changes in B leads to significant changes in the DOFX of the AX equals to B system. The condition number may be represented as the ratio of the largest and smallest eigenvalues in absolute values of a given matrix. The condition numbers are desired to be close to unity. So consider an ill-conditioned matrix equation system AX equals to B. Consider an ill-conditioned means its condition number is very high. Matrix equation system Ax equals to b. If M is a preconditioner, then M inverse Ax equals to M inverse b. This transformation known as left side preconditioning reduces the condition number of the resultant matrix M inverse A close to unity or 1. So we can similarly have right side preconditioning and both side preconditioning. So here we illustrate the right side preconditioning. Ax equals to b may be cast as a M inverse M x equals to b. This gives us a M inverse y equals to b, where mx equals to y. So find y from a M inverse y equals to b, and then find x from mx equals to y. A very common preconditioner is the diagonal preconditioner or the Jacobi preconditioner when the matrix is diagonally dominant. For diagonally dominant matrices, the diagonal terms may be considered to form a preconditioner. This preconditioner is known as the Jacobi or diagonal preconditioner. So for Ax equals to b system, M equals to Aii represents a diagonal preconditioner. The matrix capital A can be decomposed into its lower and upper components, the lower triangular matrix and the upper triangular matrix. Any of these triangular portions can also be considered as a preconditioner. Now, we introduce the concept of matrix-free methods. The matrix-free methods are mostly related to the Krylov space methods or the non-stationary iterative methods, where we involve the preconditioners. These methods are mostly used in conjunction with the non-stationary iterative methods or the optimization methods based on minimization of residuals. These methods of non-stationary type are known as the Krylov space methods. So consider a given matrix equation system Ax equals to B. By using left side preconditioning, we may write P inverse Ax equals to P inverse B, where P is the preconditioner. So this is a transformation. Now, for our calculations, we do not perform the multiplication P inverse A after constructing the full P matrix and the A matrix. In practice, P inverse A product is not performed by having full matrices P and A formed and followed by the product. For practical FEM applications, when we have large number of equations, then if we perform the assembly of the element level matrices and vectors, we get a large matrix equation system. The size of this matrix equation system is so large that even with iterative method, the computer requirement, it becomes very much demanding. For large matrices or large number of DOF, assembly of the element level matrices leads to a large sized assembled matrix that demands high memory requirement even when using iterative solvers. Therefore, the concept of matrix P method is that we do not perform the assembly. We write the element level contributions and perform our operations at the element level contribution itself. The matrix free methods use element level KE and FE data and do not combine the element data to generate the global matrix K. So, the concept of the matrix free methods we can illustrate with respect to a simple problem. So, illustration with respect to an 1D problem using two noded bar elements and GFEM. So let us consider heat conduction problem, the model problem, K d2t dx2 plus Q equals to 0, X equals to 1, X equals to 0, T equals to T1 at the left boundary and T equals to T2 at the right boundary. We discretize this domain by using 5 finite elements. So we have 5 finite elements, 1, 2, 3, 4, 5, global nodes 1, 2, 3, 4, 5, and then global node 6. This is our delta X. So this is our mesh. So these are our capital A and these are our elements. Then we generate the ID array. So we have 6 nodes. So global equation number 0 at the boundaries, equation number 1, 2, 3 and 4 within this element, internal nodes. They are having temperatures like T1, T2, T3 and then we have T4. So we can generate the ID array and LM array with respect to this picture. So ID of A equals to P. This gives us ID of IEN AE equals to P, where IEN AE equals to capital A. We have E. E is varying from 1 to 5, 1, 2, 3, 4, 5. A is varying from 1 to 2. IDOF is 1 and number of element level equations 1 and 2. So this is one arbitrary finite element, element E, local nodes 1 and 2, and the mesh size is delta X. So our equation numbers for this case per element, these are 0, 1, 1, 2, 2, 3, 3, 4 and 4, 0. So it suggests that our global matrix equation system, this will be of 4 by 4 size because we have capital P or capital Q as 4. The assembled matrix equation system is K equals to K11, K12, K13, K14, K21, K22, K23, K24, K31, K32, K33, K34, K41, K42, K43, K44. Our T is T1, T2, T3, T4 and our F is F1, F2, F3 and F4. So we have already solved problems in 1 dimension and 2 dimensions using different types of elements. The purpose of showing this example once more is to illustrate the limitation of the assembly process when the matrix size becomes very large. To show this, we take help of this simple problem with very few number of elements and nodes. So here, now we write the assembled matrix equation system. The assembled matrix equation system is, so our first term is K11. So let us go to the mesh with 6 nodes. Equation number 0, equation number 0, equation number 1, 2, 3, 4, element 1, element 2, element 3 and element 4. So these are our global equation numbers and these are our elements. So first we have K11. So K11 means this is K221 plus K112. K221 plus K112. Then we have K12. K12 is K122. K13 and K14, both of them are 0. Then K21, it will be K212. Then K22 will be K222. K222 plus K113. Then K23, it will be K123, K123 and K14, this is, and K24, this is 0. Then we have K31, it is 0. K32 equals to K213, K33 equals to K223 plus K114. K34 is K124, K41 is 0, K42 is 0, K43 is K214 and K44 is K224, K224 plus K115. This is our assembled matrix equation system. And then our degree of freedom vector is T1, T2, T3 and T4. Then our load vector is F1 is F21 plus F12 minus K211 T11. F2 is F22 plus F13. F3 is F23 plus F14. F4 is F24 plus F15 minus K125 T25. So in this case we are explicitly forming the assembled matrix equation system and the load vector. We can avoid forming K and F, but instead of K11 we can use K221 plus K112. Similarly, all the Kij terms can be represented in terms of Kije and F terms can be expressed by Fie and Kije as the case may be, based on the boundary conditions. It means that the concept of matrix-free method, it avoids explicit construction of the global matrix equation system so that there is no storage requirement for the capital F and capital K. The matrix-free methods avoid explicit formation of K and F so that calculations can be performed using the KIJE and FIE data. The storage requirement therefore reduces significantly when one goes for the matrix-free methods. So let us consider a diagonal preconditioner P. In that case, with the diagonal preconditioner, our assembled equation system, it will look like with the diagonal preconditioner, our matrix equation system will simplify to P inverse KT equals to P inverse F. Our K matrix, we have it as K221 plus K112, K221 plus K112, then it is K122 0 0, K122 0 0. In the second row it is K212, K212. The second diagonal is K222 plus K113, K222 plus K113. The next is K123, K123 0. In the third row we have K213, K213. The diagonal term is K223 plus K114, K223 plus K114. The next term is K124, K124. In the fourth row we have K214. And the last diagonal term is K224 plus K115, K224 plus K115. Then we have the degree of freedom here, T1, T2, T3, T4. Here we have the diagonal terms inverse as P inverse. So we can write it as 1 by K221 plus K112 0 0 0. In the second equation we have 0, 1 by K222 plus K113 0 0. In the third equation we have 0 0, 1 by K223 plus K114 0. In the last row we have 0 0 0, 1 by 224 plus K115. Similarly, in the right hand side, we get the same matrix P inverse. This is 1 by K221 plus K112. Then we have the terms 0, 0, 0. In the second row, we have 0, 1 by K222 plus K113, 0, 0. In the third equation, we have 0, 0, 1 by K223 plus K114, 0. And finally, in the last row, we have 0, 0, 0, 1 by K224 plus K115. This multiplied with the load vector F. So multiplied with the load vector F, F1, F2, F3, F4 that we have written in the element level. We should remember here that we actually never perform explicit product between this P inverse and K. For matrix free methods, we do not perform explicit multiplications between P inverse and K by forming the full matrix, by forming the full matrices. I conclude today's class here. In today's class, we have discussed the stationary, iterative methods such as Gauss-Seidel, Jacobi, as well as the successive over-relaxation. We have briefly introduced the concept of preconditioning for accelerating the rate of convergence in non-stationary iterative methods while dealing with large sized sparse matrices. We have also explained the concept of matrix-free methods that reduce the computer memory requirement. For today's class, I suggest the textbooks by Professors Tanhill et al. As well as Professor S. V. Patankar. Thank you very much for attending today's class.